This is the second part of the video for the notes for 1-4, and now we're going to start talking about series. So in the previous section, or the previous part, we talked about sequences, which are looking at numbers that have the same thing, either added or subtracted to get the next number, and trying to find terms in a sequence, jumping to, say, a term that's not the very next one, but maybe one that's quite far away from where you're at right now. So now we're going to flip this a little bit and we'll get series. A series is going to be the sum of your terms in some finite sequence. Finite means that it is going to end at some point. You will have a set number of terms in the sequence. It's not like, it's not something that's going to continue on together or forever. This is typically going to have, either it's going to tell you how many terms are in the sequence, or it's going to have you find how many terms there are, because it's going to give you the first and the last terms. So we have a finite series, and then specifically finite arithmetic series. There are different types of series. There's geometric series, which you multiply to get the next term in the sequence. But for today, we are still going to be adding or subtracting to get the next term. So if you're trying to find the sum, you can always add the terms together, or you can use a recursive type formula. And we're going to take a look at some of those types of examples. So here is part A of example 4. We want to know the sum of the terms in this arithmetic sequence: 1, 4, 7, 10, and 13. And then we want to find the general formula. So I know you guys can just go through and add them up, your sum in this case. And actually, I'm going to change that. Instead of writing S sub n, because we do use S for sum, I'm going to do S sub 5, because 1, 2, 3, 4, 5, there are 5 terms in the sequence. So that's 1 plus 4 plus 7 plus 10 plus 13. When you add those all together, you are going to get 35. So S sub 5 is equal to 35. So here is something interesting to look at with this. And you may not instinctively think about this whenever you're trying to find a general formula, but it is interesting to note. If we were to reverse these, so I said I have 1 plus 4 plus 7 plus 10 plus 13. If I look at the reverse, I get 13 plus 10 plus 7 plus 4 plus 1. And what do all those terms add up to? Well, 14, 14, 14, 14, and 14. So how many 14s are there? Well, there's 5 14s, but we added the sequences together, which means there was double the amount from what we had originally. So we would divide that by 2. Well, how did we get that 14? 14 happens to be the first and the last terms added together. And this is where your formula comes in. Your formula for any S sub n is going to be the number of terms in the sequence. Notice I had 5 14s, there were 5 terms in the sequence, times the first term plus the last term, and then divided by 2. Because you had double the amount, you have to divide it by 2. And that's going to be our formula that we're going to use for sum. So, what is the sum of the following arithmetic sequence? Using that sum formula, I have 1, 2, 3, 4, 5, 6. I have 6 terms. My first term is 2. My last term, which I'm going to call A6, is 22. And then we simply plug in. So S6 is going to equal 6 times 2 plus 22, and then divided by 2. So 2 plus 22 is 24. So you have 6 times 24 divided by 2. You can divide the 24 by the 2 or the 6 by 2 before you multiply them. So you can think of this as 3 times 24 or 6 times 12, but both answers are going to give you 72. And that was a whole lot quicker than actually going through and adding up the numbers in our head. So going along with series, occasionally you'll see things that are in sigma notation. Sigma notation is a way to express the sum of your sequence without actually writing out the terms. So you have a couple of things here. This weird E-looking Greek letter, that is a sigma. On the bottom, it says index I counts through the terms in the partial sum. It's a partial sum because you do have that finite amount. On the bottom, it's going to tell you what you're starting at. So typically this will be a 1, but occasionally it might be something else. So I equals 1 to n. So n on the top is going to tell you what term you're going to, and then you have a sub I. So this is going to be some type of equation, or actually an expression because it's not going to have an equal sign in it. But you might see 5i plus 2, or 7i minus 3. Whatever variable is in this part here is going to match with whatever's on the bottom. And on the top, you'll have a number. So you can see here the value of the I term is a sub I. So again, this is sigma notation. This is sigma notation. And behind my video here, I just drew a sigma. So your sigma is going to have a little hook on it, and then you're going to kind of make your E and then hook it again on the bottom. We're still going to be using the same formula to find the sum, because sigma does mean sum. So I am still finding the sum. I am still using the sum formula, which I'm going to write up here. We just need to figure out what the different parts are. So I'm starting at 1 and going to 9. That means I have 9 terms. If you were starting at a number different than 1 on the bottom, you would have to think about how many terms are actually in the sequence. 1 to 9, that includes 9 terms. A shortcut way, you would subtract top from bottom and then add 1. So 9 minus 1 is 8, plus 1, that brings me up to 9. If I was starting at 3, if I was starting at the third term in the sequence, and going from 3 to 9, 9 minus 3 is 6, plus 1 is 7. So if I started at I equals 3 and went to 9, that would actually be 7 terms. So this one has 9, so my n is 9. My first term. To find the first term, you are plugging the 1 in for the I. So 2 times 1 minus 6 is going to give me -4. To find the last term, which would be the 9th term of the sequence, I would plug in a 9. That's 2 times 9 minus 6, which is going to be 18 minus 6, which is 12. And then I can plug into my sum formula. So S9 is equal to 9 times -4 plus 12, and then the whole thing divided by 2. You are allowed to have negative terms in your sequence. There's nothing saying that you can't have that, so it is okay that one of my terms is negative here. So -4 plus 12 is going to be a positive 8. So I have 9 times 8 divided by 2, which is going to equal 36. So the sum of the terms here is going to be 36. The sigma is equal to 36. Okay, so this is part B of example 5. We're going to go backwards now. We're going to write this series using sigma notation, and then we're going to figure out what the sum is. So in order to do this, and this involves a little bit more finesse than what we've done before, you want to figure out how many terms are in the sequence. So I'm going to go back to this formula. This is the explicit formula for a sequence. And I don't know my n. I know that my last term is 79. I know my first term is 2, and my common difference is going to be 7, because I'm adding 7 to go here. but I don't actually know what my n is. I don't know how many terms are in the sequence. But if we solve this equation, we can figure that out very, very easily. So I can subtract the 2 and distribute the 7. So I have 77 equals 7n minus 7. Add the 7 over. You get 84 equals 7n, and that means your n is going to be 12. So there are 12 terms in the sequence. If you want to know what goes with the sigma, because we're going to be looking at this, we are starting at 1. I know I'm going to 12 now, but I need to figure out what's going to go off here on the side. You can actually go back to your recursive formula, and if you simplify the one side, the underline what we're talking about here, if we simplify this right-hand side, that is going to be the formula that goes over here. Typically, you don't plug it in this recursive format. 2 plus 7 times n minus 1. This is going to be 2 plus 7n minus 7. So that's going to be 7n minus 5. So 7n minus 5 is going to go there. Now the minus 5, you can actually figure that out by looking at the question, because remember how we said our common difference was 7? So this would be like the first term, the second term, the third term, all the way up to the 12th term. This -5 is your 0 term. This would almost be like your y-intercept. It's where the x is equal to 0, and x really represents what term you have. So if you don't want to do your arithmetic here by distributing your common difference and simplifying, you can actually just count backwards down to 0. So if I would have this 2, the term right before that would have to be the -5. So that's where that -5 comes in. 7, your common difference is basically like your slope, because arithmetic sequences are basically just linear functions. That's all they are. They have a slope, they have a y-intercept. It's just that we're adding them up to get a final number at the end. So finishing this out, what is the sum? Well, the sum, we do have the whole sum formula. So my formula, I'm going to scroll a little bit here. So S12 is going to equal 12 times the first plus the last, and then divided by 2. So this is going to be 12 times 81 divided by 2. So that's really 6 times 81. And I already have this written down on my paper, so I'm going to cheat a little bit, which is 486. So there we found the number of terms in a sequence. When we weren't told it, we were able to write in sigma notation, and then we were able to get the sum. The very last question is putting some real-world perspective onto this. And this one I know is not necessarily a great example, because this is kind of easy to figure out as far as common difference goes. So you have a pyramid of cans on display in a supermarket. The top row has 1 can, the second row has 2 cans, third row has 3 cans. If there's 10 rows of cans, how many total cans were used to make the pyramid? Well, because these match up so easily, the first row has 1, the second row has 2, third row has 3, the 10th row is going to have 10 cans. So to do our sum formula, we know we're going to have 10. It's going to be 1 plus 10, and then divided by 2. Now, if you couldn't easily figure out how many cans were in the 10th row, you would have to do what we did in the last question in order to figure out just how many were in that final row. So you may have to use the sequence formula, the explicit formula there. So this is 10 times 11 divided by 2. So you can think of this as 5 times 11. So total, there are 55 cans in the display. These may take a little bit of practice. I don't know how much work you've done with sequences and series before, but this is a nice, easy section that gives us a little bit of a break from graphing, which is what we've been doing previously. So please look back over the notes, rewatch any parts of the video, either this one or the previous one that you need to, and contact me if you have any questions.